Let's take another look at a problem here where we're dealing with the speed of sound. In this case, we've got an aircraft flying along. A jet passes overhead at an altitude of 500 meters. When the plane is directly overhead, the sound of its engines appears to come from a point A. Okay, so that's behind the aircraft. If the average temperature of the air is 10 degrees Celsius, how fast is the plane moving? So the first thing we need to do is determine the velocity of speed in the air. So the speed at a sound at a temperature of 10 degrees Celsius or 283 degrees Kelvin. So we need to get our Kelvin relationship so that we can use the relationships that we formed here. So the velocity then in the air, 331 meters per second, and then we have to factor in the temperature relationship. So 331 meters per second times 283, which is the speed of sound in 10 degree Celsius air, divided by 273 K for our conversion. So with that, we end up with 337 meters per second as the velocity of the sound in the air. So when the plane is at point P, out here ahead of where they hear the sound reaching the observer at the origin, O, originated at point A and has traveled some distance. So again, this is from the diagram. So the relationship between the origin and point A behind it, we can put together a trigonometric relationship. So origin to point P, we know, is 500 meters. And we know that it forms an angle from the diagram of 22 degrees. So the cosine of 22 degrees is going to give us the trigonometric relationship we need to determine the other side of the triangle. Okay, so we're just setting up our sides and angles here with what we know. So 500 meters divided by cosine 22 gives us a length of 539 meters then for the distance then from the origin to point A. So now we can calculate the transit time for this sound. So the time is equal to, again, origin to point A divided by the velocity now. So we have the velocity v sub s that we just calculated on the top here. So 539 meters divided by 3.37 meters per second gives us a time value then. Meters cancel out, we're left with seconds. 1.60 seconds is the transit time for the sound from the origin to A. In this time interval, the plane then traveled a distance from A to P. So if we look at, again, our trigonometric relationships from the origin to P, if we take the tangent now of 22 degrees, we get 500 meters times the tangent of 22 degrees, or a distance of 202 meters from A to P. So the speed of the aircraft then, the jet, is the distance A to P divided by the amount of time for the transit of the sound. So 202 meters divided by 1.6 seconds gives us a velocity of 126 meters per second is the speed of the plane. Okay, so we were able to do that, determining the side angle sides relationships and our conversions based at specific temperatures.